Hello everyone, and welcome to the lecture on an introduction to algorithm analysis and Big O. In this lecture, we're going to start off with a couple of slides explaining what this lecture and what this section is about, and then we'll jump into some live code. Let's go ahead and get started. So, first off, we need to ask ourselves, why analyze algorithms? Before we do that, we need to clarify what an algorithm is. So in this course and in general, an algorithm is simply a procedure or formula for solving a problem. So I don't want you to be intimidated by this word of algorithm, especially in an interview setting when someone asks you to come up with an algorithm. It's just a procedure or formula for solving the problem at hand. Now, some problems are famous enough that the algorithms have names, as well as some procedures being common enough, such as certain types of sorting, where the algorithm associated with it has a name, such as merge sort or bubble sort, etc. And we'll be covering those later on in this course. But now that we know what an algorithm is, we have a good question we need to answer. How do we analyze algorithms, and how can we compare algorithms against each other? So, what I want you to do is imagine if you and a friend both came up with two separate functions to sum the numbers from 0 to n. How would you compare the functions and algorithms within the functions? How would you know which one was better? How would you even define what better is? So let's jump to some live code examples to explore this further. Okay, we're here at the Jupyter Notebook, and notice I have the corresponding Jupyter Notebook available here for you in the Jupyter NB viewer, and this is the example we're going to go through. But let's go ahead and jump into a live notebook so we can code. And I'll just zoom in real quickly so you can have a better view. Okay, so let's start off. Let's say your function looked something like this. We'll call it sum1. It takes in an argument n, and we're going to take an input of n and return the sum of the numbers from 0 to n. And you decide to make an algorithm that looks like this. You set a variable called final sum and set it equal as 0 to start. Then you say for x in, and let's say range n plus 1, you say final sum plus or equal to x. And then we return the final sum. Note, we can also use xrange for Python 2 to make that into a generator. But that's not really the point here, so feel free to use either. So you have this. Let's go ahead and test it out. Sum 1 of 10, you get 55 out. So that's 0 plus 1 plus 2 plus 3 plus 4, etc., all the way to 10. So that's your algorithm and your function. Let's say your friend came up with this. We'll call it sum2, the function. And it does the same thing. It takes an input of n and returns the sum of the numbers from 0 to n. But your friend figured this out. N times n plus 1 divided by 2. Let's check if this works. We call the function on 10, and notice we get the exact same thing out. So both functions have the same result, but completely different algorithms. You'll note that the first function just iteratively adds the numbers. So iteratively, you're just adding these numbers to your final sum, while the second function makes use of this algorithm. And I'm going to jump back to the Jupyter Notebook because I have it written out here. So the sum of I from I equals 0 to n is equal to n times n plus 1 divided by 2. So what we want to do is objectively compare the algorithms. So we could compare the amount of space they take in memory, and we can also compare how much time it takes each function to run. So before we start talking about Big O notation, let's just get a general idea of what we're actually talking about here. Let's go ahead and compare how much time it takes these guys to run, these two separate functions. And what we're going to do is use some built-in magic commands in the Jupyter Notebook. So I'm going to use the timeit magic command. And we'll say the first function, sum1 100. So it looks like it takes about 3.62 microseconds per loop. Now let's check out the other algorithm. Through timeit, sum2, 100. Right now it's performing the loops. And let's see. So don't worry about this right now. This just means that a result might be being cached, but what you really want to focus on is that it's taking on an order of nanoseconds per loop. So you can see that the second function is actually much more efficient. So running at a much faster rate than the first means that this second function, or this second algorithm that the function used, sum2, is a lot more efficient. But the problem is here, we can't just use time to run as an objective measurement, because that will depend on the speed of the computer itself and hardware capabilities. So we want to use an objective method to compare how much time it takes these guys to run, both of these functions, but we want it to be hardware independent, so we can't use time. And that's where big O notation is going to come in. So we're going to be able to use this idea of big O notation to compare algorithms objectively, both in how much time they take to run and how much space they take up in memory. All right, so what we discussed in this lecture, just to go over it again, I'm going to hop over to Jupyter Notebook, is just a general idea of why analyze algorithms, how to analyze algorithms, and start getting a notion of you're going to have to do this objectively and hardware independent. So you can't use just time to run. We'll have to use big O notation. All right, that's it for this quick introduction. In the next lecture, we'll dive in more into what big O notation actually is. All right, thank you, and I'll see you there.